right, let's talk about the second mode, which is convection. So convection, definition for that is heat transfer from a surface to a moving fluid, right? So conduction, heat transfer within a solid medium. Convection is you're at the boundary of that solid medium, you're transferring heat to something that's moving. If it's solid and then you have a fluid and that fluid is static, it's still conduction, right? It's got to be moving. So where this term comes from, convection, is actually two, what do they call it, a portmanteau. So it's like two words together. So it's conduction plus advection. So conduction, you know, right? It's microscale interaction. Advection is energy movement by bulk transport. So it's a piece of fluid that gets hot and moves. That's advection. So that word together, convection, heat transfer from a surface to a moving fluid. So there's a rate equation for this. The rate equation is called Newton's law. One of like 6 Newton's law. Newton's law of cooling. It turns out Newton was a pretty busy guy. So Newton's law of cooling, Q dot convection, is equal to H bar times AS times TS minus T infinity. So let me explain what each of these are. So you recognize that there's an area, there's a temperature difference, and then there's this H bar. So H bar, this is the heat transfer coefficient. And it turns out to be an average heat transfer coefficient. So what this is saying is, let's say there's some heat transfer coefficient at a particular location on that surface, right? There's like, the heat transfer coefficient is going to depend on the geometry, on the flow, how long the flow has been developing. We'll get to that later in the class. But there's a heat transfer coefficient at some coordinate x, y on that surface. H bar is just the average over the entire surface, right? So we say H bar, our average heat transfer coefficient, covers, right, this entire surface. AS is going to be this, this surface up here. It's going to be the entire exposed surface area. So let me give you units on these. So this is watts. So H bar is watts per meter squared degree Kelvin. So it tells you per temperature difference, per area, how much heat there is, or how much heat's going to transfer. Okay, AS is your surface area. TS, AS is meters squared. TS is going to be your surface temperature. That could be, Kelvin, Celsius, whatever. It's better to stick with Kelvin pretty much for everything. So, yeah. Yeah, sorry. So it's dot. Any units that I write with a dash, it just means you're multiplying them. There are no subtracted units as far as I'm aware. So this would be meters squared dot Kelvin. Okay, and then T infinity, this is what we call the free stream temperature. Again, that's going to be units of Kelvin. All right, so you kind of stare at this, it makes sense. You see you're predicting a rate of heat transfer. You have a heat transfer coefficient that gives you units of watts per meter squared Kelvin. Multiply that by an area, the meter squared goes away. Multiply that by a temperature difference, and you get watts. Right, so it's pretty straightforward.
What did you write in the parentheses for heat transfer coefficient?
That's watts per meter, average, yep, average. Other questions on convection? So, yeah, go ahead.
Is the free stream temperature like the ambient temperature?
Yeah, right. So think of it like you're physically in a room, the wind's blowing over you, it's the temperature of the wind, right? It's the thing, it's the sink in the cold, it's the cold reservoir. It's the thing that the heat's going to. Okay?
So does this also work
Yes. Or you could have a negative Q dot there, for sure. Okay, so for these rate equations that I'm giving you, like we're going to go, right away we're going to go into a lot of detail on the conduction part. For convection and radiation, I'm pretty much going to give these rate equations. You just take them as gospel for now. And then later in the semester, we're going to revisit like how you compute H. Right? H, I'll give it to you for now. Later on, you'd be able to compute that yourself. Okay, last thing here, radiation. So this is our third mode of heat transfer. Definition is, this is heat transfer via electromagnetic waves, photons or whatever, from surface A to surface B at a distance. So this is a very different mechanism. Conduction, convection, convection is basically conduction, just with a little bit of extra stuff going on. Radiation is very different, right? It's just a different phenomenon. You have a state change of an electron, it emits a photon, that photon just zooms off into space. Eventually, it hits something else, and that causes heat transfer. So in this example, I mean, we can model this in a really simplistic way. It's a very complicated, nuanced phenomenon, but in terms of heat transfer, there's a pretty simple rate equation that we're going to use. So let's see, for this one, the rate equation is as follows. So, by the way, this is called the Stefan-Boltzmann equation. Remind me not to use microphone 1 next time. Okay. Stefan-Boltzmann equation. So the equation here is Q dot radiation is equal to sigma times epsilon times AS times the temperature difference is TS minus T infinity, sort of. It's not actually TS minus T infinity, it's something else. It's TS minus T infinity, each of them to the 4th power. Okay? So there's a huge importance of temperature in radiation. At room temperature, very little radiation occurring. At sun temperature, a huge amount of radiation occurring. Okay. So in this case, let me give you other stuff here that you need. So this is, sigma is the Stefan-Boltzmann constant. Just abbreviate it SB. That has a particular value. It's 5.67 times 10 to the minus 8th. That is, I will guarantee you, the easiest constant to remember that you'll ever have. 5.670 to the minus 8. And the units on that are watts per meter squared, Kelvin to the 4th. Right, watts per meter squared, Kelvin to the 4th. Epsilon, that's the surface emissivity. Right, this is a property. It's a property that depends on temperature, but it's often just given to you. You say like, okay, emissivity of 0.9 or something, right? It's a number between 0 and 1, and it's an indication of how much of the potential radiation is actually emitted. All right, last couple things, and then we'll finish up here. AS is the surface area of the emitting surface. Okay, again in meters squared. TS is surface temperature. And then T infinity is like the ambient or surrounding temperature. Okay, it's really important for this particular equation that you use units of Kelvin, right? Temperature has to be in units of Kelvin. If you do it in Celsius, it's wrong, okay? So I guess we'll leave it there. I already kept you a minute late, but you want to come up and talk. All right, thanks everyone. We'll see you on Monday.